Okay, so hello everyone. I think we finished the introductory for the power series. So power series, it's supposed to be 11.8 in the textbook. We still have two more sections, which is 11.9 and 11.10. And I think I can say that we've done the chapter 11 if we finish up until the 11.10, which is the Taylor series and the McLaurin series. I think I will skip the approximation on the 11.11, so I will just finish on the Taylor series and McLaurin series. And I think if we finish chapter 11, I will review a little on factors, but I think I will focus on the last part on the factors, two sections on the factors, the last part, and finishing chapter 12. And if we still have time, I will move to chapter 13. But if not, then maybe the timing for the midterm exam. So it will be chapter 10, the parametric and the polar, chapter 11, and a little bit chapter 12. Okay, so maybe it will be around end of October. Since our class that has 2 hours only Friday, so maybe the best schedule is Friday morning. Because we don't have any other classes unless we maybe find another time, which I think depends on the classroom. Okay, I can get the classroom because I think we have around 20 something in the class, right? Around 20. I think this is maybe 2/3, right? So yeah, maybe 20 something. So I need to find a class. I think 20 something is easy to find a classroom, but I'm not sure I can get the schedule. And then I need to match the schedule with you, right? So I think the best way is Friday morning. So maybe the end of October is around, let me check maybe it will be 27. Okay, 27. So around 2 weeks. So hopefully I can finish the chapter 11 early so that I can review and maybe preparing some works for you. And for Monday's class, for your TA class, for next week, it will be, I will teach on the TA class, right? Because TA last week having 2 classes, right? So next Monday morning, I will come into the class, okay? And yeah, your TA class will be started next 2 weeks, okay? So I think we can finish early for the chapter 11. Okay, now from the power series, we're going to move to 11.9, which is the representation of function as a power series. So to begin with, we know that we have the geometric series as I also mentioned yesterday. So we can take this as like a geometric like that. And let me rewrite again that we have ratio, that if we want to make it converge, the ratio needs to be less than 1. Okay, so this is the r, we multiply with r, multiply with r. R is equal to x. Right? So r is x, and r need to be less than 1 so that we can get converge results, right? Converges. Which means we need to make the x is less than 1. Or we can also remember that to find the total sum for this geometric series for the convergent that is r is less than 1, we have a over 1 minus r, which we can implement a as 1, and then r is x. Okay. So this 1 over 1 minus x we can treat like a regular function, and we can define this using our geometric series. So we can write that this 1 over 1 minus x, it is a representation function for the series for this x with power of n. So we can write this is equal to 1. I'm not sure what's happening. Okay. So 1 plus x squared plus x cubed plus dot dot dot. And of course this is going to be less than 1 for x. Okay. Really trouble. I think the cable, I need to check. So this function, we call this is the representation function for the series. And if we would like to somehow to check, okay, from the series, okay, so let me write here. So if we check the partial sum Sn of x, okay, so we can write and rearrange. For example, for n, we can have 1 plus x squared plus let's say x cubed plus dot 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 plus x with power of n. Okay, and then we can set up for each of n, like from 1, 2, 3, and we could see that we can rearrange. This is from 1 plus x, and then we can set another one, which is 1 plus x squared, and then we can set up more and more. Okay. And imagine that if we increase the n, the functions will also increase. We will also adding a new variable which is higher, 1 degree higher than the previous one, right? So if we take x3, we have x cubed. If we have s4, we have x cubed, x4, right? x power of 4. And we see that if we are going to take the n increase, so that n is increase, this Sn will approximate the function of x. Okay, so if we take the curve for each of these functions, this is all the function based on the partial sum. Okay, so this S2, if you look on the curve here, this S2 is actually 1 plus x squared. This is actually just a quadratic function, so it's quadratic function. And then we have the power of 5, power of 8, power of 11, and if we are considering just this interval, this -1 to 1, we see that as we getting increasing and increasing, they are actually getting somewhere. Right? They are actually so you can imagine from S2 we increase, maybe S3 will be here, and then 4, 5, and then 8, 11, and maybe if you increase S20, maybe it will getting closer and closer to this f. Okay? This f is the real functions. Okay? So this red color here is the real functions of the 1 over 1 minus x. Okay? So we could take approximation from this s. Okay? As we increase the n, and then we could touch almost touching the f of x, okay? Or maybe getting closer to this f. Okay? So this is let me write some note that this is f of x equal 1 over 1 minus x and sum of its partial sum. Now after we see how it looks like in the visuals, in the graphics, now we have these functions. Okay? So the curve is just showing you that using the partial sum, which is representing the series, if we increase the number, it is true that it will reach out these functions, which is, we say that this is representation functions of the series, the power series, and the power series of this geometric one. Okay, now how do we apply these functions? So if we want to apply, so whenever we see this, we could rewrite, or we could add this. So every time we see this, then this is actually our sum of x with power of n. Okay. So any functions that somehow you can manipulate, you can play with within this structure, you can convert this to the series. Okay. For example, if we can write this, let's say example 1 over 1 plus x squared. Okay, we have that. Okay. If we look on the structure, it's very similar to 1 over 1 minus x. So we can make 1 over 1 minus x squared. Okay, so that it could be similar to what we have here. So we could rewrite this in terms of 1 minus x squared. Okay, so then we could have a sum of, this is becoming negative x squared and then with power of n. Okay. Or if we want to simplify this in more okay. So if we can simplify this, maybe let me write a little bit left. So we can write this as sum. We can take out the negative 1 with power of n, and then x, and then with power of 2n. So this will be, we can write maybe some terms. So take 0, so 1 minus x squared plus x with power of 4 minus x with power of 6 plus x. And it become the geometric, right? It can become geometric series. And usually, maybe if the question is still asking like radius of convergence or interval of convergence, then we could say this will converge. Okay, this will converge when the ratio, or in this case negative x squared in absolute value, is less than 1. Or we could say this x squared is less than 1. And also, if you would like to take the ratio test to check the radius of convergence, it's also possible. Now, another example. Okay, let me wait for a moment. Now let's add in more. So let's try another one. So example, we have 1 over x plus 2. So we would like to know what will be the series. Okay? Or maybe let me write here. The question is find a power series representation. Okay, so for this one, and the second one is x cubed over x plus 2. So let's start from the first one. So the idea, okay, we would like to have 1 over 1 minus x, because 1 over 1 minus x is the sum, okay, and it's going to be the same everywhere. Okay, so we would like to have this, the structure. So we would like to force this one, this x plus 2, becoming this 1 minus x. Okay, so what do we do? So first is we could make this, because it has a constant 2, this is 1, maybe we could factor out this 2. Okay? So let's say we factor out 2. So 2 become 1 plus x over 2, right? Okay. And then, because we would like to have minus instead of positive, instead of plus, then we could write minus and then minus x over 2. Okay. And then we can separate the constant 1 over 2. So we could take 1 over 2, and then we have 1 over 1 minus x over 2. So we could write the sum. Now we have negative x over 2 with power of n. Okay, so that's the structure. So now we have the structure similar to what we have on the x with power of n. And we can further to simplify it. So 2 and then 2 power n, we have 2 n plus 1, and then x with power of n, or maybe let me write closer like that. And if you are asking converge, so it's going to be converge when the ratio, which is negative x over 2, is less than 1. Or if you would like to write, we can write this is less than 2. So interval, or let me just write with I, will be negative 2 to 2. Okay. Now the second one is actually, if you look closely, it has the same x plus 2, right? It's the same x plus 2. So we can write actually this x cubed. So we can write x cubed multiply with 1 over x plus 2, like that. Okay. And this 1 over x plus 2, we have defined already within this sum. So we could just multiply the x cubed with this sum. It's the same with the 1 over x plus 2, right? Okay. So we could change that. And multiply with the sum. Okay. And then we could write so x cubed over x plus 2 is equal. So we are going to combine this. So sum negative 1 with power of n. So x n plus 3 divided by 2 with power of n plus 1. Okay, sometimes you would like to write with a clean or clear n. So it has n plus 3. So we could minus 3, so we can minus everything here. So we can also write alternative. We can write sum. So we are going to minus 3 all of this, so n minus 2, x with power of n, and then negative 1, and minus 1, because I think if you minus 3, should be n minus 3, which is the same deal with n minus 1, right? If we take 0, you can check if it's okay or not. Because I think the possibility for the n for the power of negative 1 is just n and n minus 1, whether it's going to be positive or negative. The first term is negative or positive. Okay. Okay. Okay, now after we know how to find the structure, another way to relate this representation. So everything within these sections, they are all using the same 1 over 1 minus x. All the 11.9, they are all always using this, the power series of x to the power of n. Okay. Another way to set up this representation is using the derivatives or integrals of that 1 over 1 minus x. Okay. So we can write some theorem. Okay, so I forgot to put here, so let me just write so theorem. So if we have power series, we have Cn with a coefficient and then x minus a with power of n. It has radius positive, okay. Then function f, okay, defined by, let me write the definition of x. The coefficient, c is coefficient, okay. Or we could write this is the sum So we need to set up some assumption that this f is differentiable. And therefore, if it is differentiable, it should be continuous, right? So on interval a minus r, a plus r, and then we can set up that first, if we take derivative of this f, then this will be c1 plus, so we are going to just derive the whole thing, so 2c2 and then x minus a, and if we have another cubic, then it will be 3c3 x minus a squared and so on, and we can write this as the sum. And notice that the n will be different because we derive the terms. So n, cn, and then x minus a, and then n minus 1. And then second, we could also integrate the function. So if we integrate, we are going to introduce a new constant. So let's write a c in the front plus c0 x minus a, and then c1 x minus a squared over 2, and then plus c2 x minus a cubed, and this will be over 3. And plus we could write this as a constant plus this terms becomes sum of the cn and then x minus a n plus 1, because we are adding 1 for the integrations, and then this will be n plus 1. So every terms is getting n plus 1. So what's the implications for this theorem? Okay, so basically it says that if we know the functions is, for example, related somehow derivative or integration with the 1 over 1 minus x, then perhaps we could try to take these two structure and then try to find out what series the function will be. For example, right here. So example, we have 1 over 1 minus x and then squared. If we think closely, this could be from 1 over x if we derive. Perhaps it could be half the square, right? So, and then it has this 1 minus x, so we need to think what is the or let me start with the 1 over 1 minus x. So we start with 1 over 1 minus x, which is, we can relate to always to this geometric formula. And if we differentiate this, so if we differentiate, okay, so 1 over 1 minus x, if we differentiate 1 over x, okay, this will be negative 1 over x squared, right? Okay, and now we have 1 over 1 minus. Okay. So if we differentiate this, it will be minus, but we multiply with another minus from this 1 minus x. Okay. So this actually, go right here, just to refresh your calculus 1. So if we take this, then it's actually 1 minus x squared, but multiply with negative 1. So it will be a positive. So this will be 1 over 1 minus x squared. There's a reason why the example using 1 minus x, okay? Because if we derive it's still a positive, we can still see this not too complicated. If we are having minus, probably we are having different structure, right? And then all the terms are going to be derived. 1 will be 0, so x will be 1 plus 2x and then plus perhaps 3x squared. And then we can also derive the series. So if we derive the series, this will be n, x, n minus 1. Okay. If we want, we can also replace this. If we would like to have the n start from 0, for example, so we can write is equal to, so from n equal 1 we make it into 0. So what will happen to the other n? So we are replacing n with n plus 1, right? So this will be n plus 1, and then this will be x, n. So we plus 1. They are the same, okay? They are the same. Okay, any questions? Okay. So this is relating the 1/1 minus x with its derivative. Okay. But another case is if we can also take the integration parts. So for the integrations, the example will be, let me write in a new page. So another example is the ln 1 plus x. So every functions that is related to these sections, they are all connected to 1/1 minus x. So let me write here. So always, the representation function is always related to 1/1 minus x. Okay, now we have ln 1 plus x. So perhaps we can start from 1 plus x. Okay. So 1 plus x, if we write in terms of the 1/1 plus x, we see that we have an alternate series. Okay. And then if we integrate 1 plus x dx, we can get ln 1 plus x, right? Okay. We usually write with absolute value, right? But I'm removing the absolute value because I know that this should be positive. Okay. Now we can say that this ln need to be equal with the integration of this series here. So let me write. This will be 1 minus x plus x squared minus x cubed plus this dx. So this will be x minus x squared over 2 plus x cubed over 3 minus x power 4 over 4 plus and then don't forget to plus the constant at the end. Now this first few terms we can identify the structure, identify the patterns. So we can write sum. This will be alternate series which start with positive terms, so n minus 1 like that. And actually you can start from n equal 1 or 0, but I will start with 1 first because it has the x at the beginning. So this will be x with power of n, right? 1, 2, 3, 4. And then the bottom side is 1, 2, 3, 4, so it will be n. And this will be plus c. So the ln 1 plus x, the equal with this. So if you have know before we will have the Taylor series, Maclaurin series. This representation function is actually like an introduction to the Taylor series, Maclaurin series, which more general and cover a lot of functions. Okay. This is just some let's say, how we engineer the functions and make it into a series, or how to read the series and then make it into a function. Okay, maybe one more example, and then I think I will finish the class. Okay. So another example that is quite common is the tangent x. Oh, tangent inverse x. Sorry. So what will be the series for the tangent inverse? So this is probably, we need to take some time to relate tangent inverse with this structure. So again, we are always relating all the functions that is possible within this section with this. So we are going to relate the tangent inverse with 1 over 1 minus x. I hope most of you know the tangent inverse is related to 1 over 1 plus x squared, right? So if you remember, if we have the integrations of the 1 over 1 plus x squared dx, this will be equal to the tangent inverse x, right? Okay, and so this 1 over 1 plus x squared, this is actually the same structure with this, and we have done this at the previous page. So I will just rewrite for you. So we could say that this will be integrations from this structure here dx. So integrate all the components inside, just a few terms, and then you can just add plus dot dot dot. Okay. So constant plus x minus x cubed over 3 plus x5 over 5 minus x to the power of 7 over 7. So it's alternating, and then you will see it has an odd number, right? 1, 3, 5, 7. Okay. So we have the tangent inverse x will be equal to the sum or maybe before conclusions, we can set. So we can set the, let's say, the tangent inverse x. So we can set x equals 0. Okay. So everything will be 0, right? Everything include x will be 0. And tangent inverse x, when x0 is also 0. So we could know that the c will be also 0. Okay. So we can ignore the constant, okay, because it is 0. Okay. Now we can set the alternate series. So -1 with power of, I think we can just end because it starts from positive terms, right? And we start from 0. Okay. And then the component will be an odd numbers, 1, 3, 5, 7. So the bottom side will be just 2 and plus 1. Remember, we start from 0, so we can check. So 0 is 1. If n equal 1 is 3, okay, that is correct. And the x also with power of this odd number. Okay. Now keep in mind, for all the functions that we already have the power series approach, later on when we deal with the Taylor series and Maclaurin series, they are actually have the same conclusions. Okay. So the one that we've done, like the ln1 plus x, tangent inverse x, the conclusions they are the same one. Okay. If we later we observe the Taylor series and Maclaurin. Okay. Okay, I think I will finish up on here. Okay. So the next part is maybe review a little bit how we can try to manipulate the function and write down the series, and then after that we can move to the last part, which is the Taylor series and Maclaurin series. Last part on the chapter 11. Okay, and after that we can have some examples and exercise as well. Okay, so